afternoon, sir. My project for the science festival is analysis of black holes. Now, what do you think when you hear the term black hole? You would obviously think that it's a gigantic object which which sucks in everything it comes in contact with. Well, a star which is sufficiently massive and compact would have such a strong gravitational field that not even light could escape. And light emitted from the surface of the star would be dragged back by the star's gravitational attraction. There would be numerous stars like this, but we would not be able to see them because no light would reach us. Such objects are called black holes because that's what they are, black voids in space. Now, if you want a particular definition of a black hole, I would give it. A black hole is a region in space-time from which nothing, not even particles, electromagnetic waves, not even light could escape it. Now, why can't light escape? According to Albert Einstein, he described gravity as a curve in space that wraps around a body, such as a star or planet. If another object is nearby, it gets pulled into the curve. So the black hole is so dense that it creates a deep bend in space or time. Now, how we will visualize it? Take a cloth, a normal cloth. You can take any cloth. Uh, Maybe it will be better if it's just a large cloth. Take a metal ball and place it in the center of the cloth. Now you will see that it creates a bend in the cloth in the center of it. Now take small marbles and push it along the cloth. You will see that instead of linear motion, the ball follows a circular motion, a rotational motion, because of the bend created in the cloth. So that is what is a black hole. Nothing can travel faster than the speed of the light. And if light cannot escape the black hole's gravitational attraction, then nothing can. One can only escape a black hole if it travels than the speed of light, which is not possible by today's means. So, we can say that a black hole is a cosmic body of extremely intense gravity from which even light cannot escape. Black holes usually cannot be observed directly, but they can be observed by the effect of their enormous gravitational fields on nearby matter. Now, before understanding a black hole, we have to understand how a black hole is formed. To understand how a black hole might have formed, we first need to understand the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen atoms, starts to collapse in on itself due to its gravitational attraction. As it contracts, the atoms of the gas collide with each other more. The gas heats up. Eventually, the gas will be so hot that when they collide, they will no longer bounce off and instead merge to form helium atoms. Which is what constitutes an atom bomb, the principal nuclear fusion. It is also what makes the stars shine. Would eventually burn for a long period of time. But however, the star would come to an end of his fuel, and when its fuel ends, it would start to contract and would eventually settle into an object known as a white dwarf. When a star becomes small, its matter particles get very close to each other. But the Pauli exclusion principle states that two particles cannot have both the same position and the same velocity. This makes them move away from each other, and so makes the star expand. A star can therefore maintain itself at a constant radius by the balance between the attraction of gravity and the repulsion that rises from the exclusion principle. However, Chandrasekhar realized that there is a limit till which it can expand. He calculated that a cold star with more than about one and a half of the mass of the Sun would not be able to support itself against its own gravity. This mass is now also known as the Chandrasekhar limit. The Chandrasekhar limit is the maximum mass of a stable white dwarf star, which is about 2.765 into 10 to the power 30 kg. If a star's mass is less than the Chandrasekhar limit, it would eventually stop contracting and settle down as a white dwarf. The white dwarf is supported by the exclusion principle repulsion between the electrons in its matter mass above than the Chandrasekhar limit, on the other hand, had a problem with them. When they come to the end of their fuel, Chandrasekhar has shown that the exclusion principle could not stop the collapse of the stars more massive than the Chandrasekhar limit. So, if a star's mass at the end of its nuclear fuel exceeds the Chandrasekhar limit, it would collapse under its own gravitational force and would give birth to a black hole. So, we can say that a black hole can be formed by the death of a star. The crushing weight of the constituent matter falling in all from direct comparison to the dying star to a point of zero volume and infinite density called the singularity. Now let's come to the properties of a black hole. We now know what is a black hole. Let's come to the properties of black hole. The event horizon. The boundary of an black hole is called the event horizon. It is a boundary in space-time through which light and particles can only pass inwards the black hole, and nothing can escape from inside the event horizon. Travels less than the speed of light would not be able to escape the event horizon. The name refers to the impossibility of witnessing any event taking place inside that border, the event beyond which one cannot see. Say that one has a set of events in a region of space-time from which nothing can escape to reach the distant observer. The distant observer clocks near the black hole would appear to tick more slowly than those further away from the black hole. This phenomena is known as gravitational time dilation. Suppose an astronaut on the surface of a collapsing star sent a signal every second. Imagine you are his companion in the spaceship. According to his watch, to his spaceship orbiting the star, at some time in his watch, say 11 o'clock, the star would shrink below the critical radius in which the gravitational field becomes so strong that the signals would no longer reach the spaceship. His companions watching from the spaceship would find the intervals between successive signals from an astronaut getting longer and longer as 11 o'clock approached. However, the effect would be very small before 10:59:59. They would have to wait only very slightly more than a second between the astronaut's 10:59:58 signal and the one he sent when his watch read 10:59:59. But they would have to wait forever between the 11 o'clock signal. The light waves emitted from the surface of the star between 10:59:59 and 11 o'clock by the astronomer's watch would be spread out over an infinite period of time, as seen from the spaceship. The time interval between the arrival of successive waves at a spaceship would get longer and longer, and so the light from the star would appear redder and redder and fainter and fainter. Eventually, the star would be so dim that it would be no longer be seen from the spaceship. So an object falling into a black hole would appear to slow down as it approaches the event horizon and takes an infinite time to reach it. But it's only for the observer at a distance. It's only for you. While the falling body, time would still be the same. His clock will work the same. Reddening and dimming of the light is due to a phenomenon called gravitational redshift. Now let's come to singularity. What is at the middle of the black hole or at the center of the black hole? There must be something at the center of the black hole. According to general relativity, the center of the black hole then may lie a gravitational singularity. At the singularity, the laws of science and physics and the ability to predict the future would break down. It is a region where space-time becomes infinite. However, there are two kinds of singularity. For non-rotating black holes, it is a singularity. On the other hand, for the rotating black holes, it may be a ringularity. The singularity may form in a form of ring, which is called the ringularity. Two possibilities: an object which falls into the black hole in a non-rotating one, in non-rotating black hole, it would eventually reach a singularity and would get crushed under its infinite density. But in case of a rotating black hole, the singularity would take the form of a ringularity, it, in which the object may not be crushed but instead would travel through a wormhole. In this case, the black hole would act as a wormhole and would open many possibilities to travel in space and time. Apart from this, It can also result in phenomenon like time travel. However, it's only a theory of a theory, and object would get torn apart by the gravitational tidal forces and surely vaporize before reaching the singularity or the singularity. Come to the photon sphere and accretion disk. A photon sphere. What is a photon sphere? Due to the gravitational effect of the black hole, the photons are forced to travel in an orbit. To now descend to the photon sphere. A photon sphere is a location of gravity so strong that light can travel in circles. It would take a circular path around the black hole. Photons orbit the black hole at the distance of a photon sphere. A photon could leave the back of your head, go once around the black hole, and can be seen by your eye. You can see the back of your head. It is located from further from the center of a black hole, even further from the event horizon. It's a region where light is trapped, while light can still escape. Any light that you see may be emitted by the object between the photon sphere and the event horizon. On the other hand, accretion disk. Materials such as gas, dust, and other stellar objects, stellar debris, that has come close to the black hole but quite not fallen into it, forms a flattened band of spinning matter around the event horizon called the accretion disk. Although no one has ever actually seen a black hole or even its event horizon, this accretion disk can be seen because the spinning particles are accelerated to tremendous speeds by the huge gravity of the black hole, releasing heat and powerful X rays, gamma rays out in the universe as they smash into each other. There are many black holes, but they are classified into types. There are mainly four types: the interstellar black holes, supermassive black holes, intermediate black holes, and the miniature black holes. Stellar black holes are the black holes whose mass ranges from 5 to several tenths of solar masses. They are formed by the collapse of a star. When such a thing happens, it is known as a supernova. The smaller the supermassive black holes, they are smaller than supermassive black holes, and they are stretched about 20 to 100 miles across. They roam around the space. Supermassive black holes are enormous and mostly lie at the center of large galaxy. Even our galaxy has one too. They are stretched across millions and millions of miles. Their mass ranges from millions and billions of times the mass of the sun. Intermediate black holes. Those black holes' masses are more than a stellar black hole, but less than a supermassive, and they range from 10 to the power 3 to 10 to the power 6 solar masses. Miniature micro black holes. There are many black holes that are hypothetically tiny, according to Stephen Hawking. Black holes smaller than the stellar black holes may exist, and they are mainly primordial black holes, which we will come in this in this future session. So now we know that what a black hole is constituted of, or its structure. We know all about singularity, the event horizon, photon sphere. Now let's see that how do black holes grow this big? How does this monstrous and enormous object grow this big? Black holes grow by what they absorb, which means that they grow by absorbing other matter. Anything that passes the event horizon is unable to escape the black hole, so the mass of the objects gets added to that of the mass of the black hole. However, half of that mass gets emitted in form of radiation. They merge with objects such as stars, and the mass of the star gets added to that black hole. They even grow by merging with other black holes. Black holes grow by two methods: either they absorb the nearby matter or merge with other celestial objects. Now, we are talking about black holes. So I don't talk about this. If I don't talk about this, then I don't know what I will talk about. Now come to the two types of black holes: rotating black holes and non-rotating black holes. Non-rotating black holes are called Schwarzschild black holes. Sorry if I'm pronouncing it wrong, but Carl, Carl Schwarzschild was a German physicist and astronomer who gave the exact solution to Einstein field equation of general relativity. Schwarzschild black hole is a non-rotating black hole. It has neither electric charge nor angular momentum. The only distinguishable feature is its mass. Black hole would be perfectly round. Schwarzschild radius is the radius between the event horizon and the singularity of a non-rotating black hole. It is also called as or it is also called as the gravitational radius. It's given as where r is the Schwarzschild radius, g is the gravitational constant, and m is the mass of the object, and c is the speed of light. Is the It is the radius of a spherical boundary within which the given mass of a star must collapse to become a black hole. The Kerr-Newman or the rotating black hole. This type of black hole consists of both angular momentum and electric charge, although it has mass. It's not possible for a black hole to exist without mass. Although it does have mass, however, unlike static black holes, they are a bit oval in shape and consist of a region called ergosphere. Now, what you may ask, what is an ergosphere? Now, in the region of space-time, ergosphere is a region in space-time in which it is impossible to stand still. It is a result of frame dragging. As Einstein's general relativity predicted, when the mass rotates, it drags along the space-time, which it with which it affects the objects around it. Any object around it would start moving in the direction of rotation. However, around the black hole, this effect is very strong. An object would need to travel at the speed of light in the opposite direction of the rotation to escape it. Now we come to the mass of a black hole. Every black hole has mass, and so is the black hole. It's one of the three parameters of a black hole. Black hole can be of millions and billions of solar masses. It depends of how massive the star it came from was. Uh, Now we can calculate the mass of a black hole or the mass of an object by by observing the surrounding objects orbiting it. There are many methods, but I will only describe one. We can calculate the mass of the black hole by observing the objects rotating around it. But instead, I will use Kepler's third law, which states that the square of the orbital periods of the planets are directly proportional to the cubes. This is not necessary. So let's say that the star is orbiting around an unknown object because we don't know what the object is or we can't see it. So let us take it as an unknown object. Let us say that the object orbits for 60 days and the radius of this orbit is 45 AUs. Now we can use the Kepler's third law to determine the mass of the object. Now remember what the law says, that the sum of the mass of the star and the mass of the unknown object is going to be equal to the radius of the object cubed divided by the period squared. We know that the period in 60 days, which means that 60 by 365 years, which gives 0.1643 years, and the mass of the object and the mass of the unknown object are equal to the 45 AUs to the power 3 by 3 by 0.1643 to the power 2 is equals to 91.0.125 by 2.7 into 10 to the power minus 3 is equals to 3.4 into 10 to the power 6 solar masses. Anything that got to be at 10 to the power 6 solar masses got to be a black hole for sure. We earlier discussed that anything that has mass would create some effect on the space-time fabric. The black hole must also create an effect. As predicted by the general relativity, the presence of mass deforms space-time in such a way that the paths taken by particles bend towards the mass which I stated earlier. At the event horizon of black hole, this deformation becomes so strong that there is no paths that lead away from the black hole. Anything with mass, including your body, bends the four-dimensional cosmic grid. The wrap in turn creates the effect of gravity, redirecting the path of the objects that travel into it. So you can imagine what will happen in the fabric of space-time if a black hole of millions and billions of solar masses is placed there. Now let's come to the interesting part, which is one of the most interesting thing I discovered. Hawking radiation. In 1973, when Stephen Hawking visited Moscow, he was conceived by two leading Soviet scientists, Yakov Zeldovich and Alexander Stravinsky. According to the quantum mechanical uncertainty principle, rotating black holes should emit particles. However, when Hawking calculated, it is found out that not only rotating but also non-rotating black holes emit particles. Now, in an empty space, space cannot be completely empty because that would mean that the fields of the gravitational field and the electromagnetic field would zero. So in empty space, the field cannot be fixed at zero because the precise value and the precise rate of change would be zero. Instead, there is a certain amount of uncertainty and the quantum fluctuations in the value of field. You can think of these fluctuations as pairs of particles of light or gravity that appear together at the same time. move apart, and then come together again and annihilate each other. These particles are called virtual particles. Unlike real particles, they cannot be observed directly with a particle detector. By conservation of energy, only one particle would have positive energy and other would have negative energy. However, the negative one is said to be short-lived, so it wants to annihilate its other particle, but other partner. But the gravitational field inside a black hole is so strong that even a real particle can have a negative particle there. Therefore, if a virtual particle with negative particle falls in there and becomes a real particle, if that happens, it no longer has to annihilate its partner. Its partner can fall into a black hole or either get thrown out, slingshotted out of the black hole because it is positive. For an observer, the smaller the black hole, the less it has to travel to reach the singularity and become a real particle. Thus, the rate of emission will be higher and the temperature of black hole will be higher. Therefore, the smaller the black hole, the greater its temperature. The more it emits, the more it loses. Now, to the particular definition of the Hawking radiation. Hawking radiation is the thermal radiation predicted to be spontaneously emitted by the black holes. It arises from the steady conversion by quantum vacuum fluctuations into passive particles, one of which escapes at infinity while the other is trapped in the horizon. Primordial black holes. Now, I have stated earlier the smallest black holes may be the primordial black holes. The primordial black hole is a type of black hole that is formed after the Big Bang. They're formed by high densities and sufficiently dense regions in the to undergo gravitational collapse. Since they are not formed by collapsing of gigantic stars, their mass is lower than 10 to the 11. In order to observe a primordial black hole, one would have to detect several gamma ray quanta coming from the same direction within the reasonable space of time. Now, how can we believe that such a thing exists? I have said so much about these. How could one believe in objects for which the only evidence was calculations based on theory of general relativity? However, we are now at an age where the existence of black holes has already been proven, and I don't have to prove them. Pictures of them. Not exactly a picture, because if it's invisible, how can we see it? If no light escapes it, how can we see it? Well, we can't see the black hole since no light is able to escape them, but we can observe their effects on the nearby objects. To confirm the presence of invisible black hole, astronomers used a method called gravitational lensing. This method works on the concept of Albert Einstein's general theory of relativity, which says that light bends when it travels past a massive object. The astronomers noted that the light from the distant stars was magnified for a brief time, suggesting there was an object in front of the star but was not visible. We can also detect them by detecting the gravitational waves from merging black holes and the notion of the black hole. Now, with this, a black one will believe that a black hole just just bonds and stays forever. But no, everything has an end. It's the universal law. So, as a black hole. End of a black hole. We come now to the end. According to the general relativity, black hole exists, but Stephen Hawking found out that black holes emit radiations, which are now known as Hawking radiation, as stated earlier. Eventually, as they radiate, they lose mass and shrink, and eventually they evaporate. It is not faster. They only um, emit one particle per year. A good sized black hole, say a few times more massive than the sun, will take about 10 to the power 100 years to eventually evaporate through the process of the Hawking radiation. But eventually, it would come to an end. So that was my project. I would um, like to add more things, but I don't think that it will be a very long thing. It's already long. So I don't know. Thank you.